And then it's
That's fair, right?
So that's not going to be less than 3 days.
Yeah.
Ready? Yeah, we're ready. Are we? Yeah. All right, welcome everybody. It is my great pleasure to introduce Nicolas Sartore, who joined us pretty much exactly 2 years ago, just over, from France. He did his undergraduate in physics at Paris-Saclay and a master's in geoscience at the École Normale Supérieure. So he's got all the right credentials to tackle a tricky problem like this. This work, as he'll tell us, is part of an SF project, and he is also together with Clark, first PhD students in my group, and so this is the first time I'm doing this type of introduction, and I'm very excited to hear what he has to say, and I'm more excited for you guys to hear this. All right.
Thank you, Phil. Can you hear me in the back? Yep, good. So, hi everyone, thanks for coming to today's talk. I'm going to present my research for the last 2 years, which is about the Ross ice shelf and its foods. Don't worry, I will explain quite quickly what is the food, but before I want to do some context with an introduction, when I'm going to define what an ice shelf is, what we mean when we say rainfall mode bending, and what are the causes of this bending. So this is a map of Antarctica. All these white areas that you see here in plain white are an ice shelf. There is around 50 of them, and if you sum up their area, they run to 1.5 million kilometers square, which is around 10% of the surface of Antarctica. And these ice shelves are really important because they drive most of the mass loss of Antarctica that end up leading to sea level rise. So before anything else, this is a diagram they made, which is with an ice sheet on the left and an ice shelf on the right. The ice sheet is always grounded, it means it touches the ground, and when the thickness goes below a certain threshold, it starts to float and so rise, and this is what we see here. And that's from the point we call it an ice shelf. And the line between the two defines what the difference between the ice sheet and the ice shelf. And when I will say front, I will mean this part of the ice shelf at the end, which is always in contact with the ocean. The ice flow is always from the ice sheet to the ice shelf, and there is two main processes that remove material from the ice shelf. The first one is called melting. Melting can happen at the top of the ice shelf, creating lakes or rivers. It can happen at the base of the ice shelf. Because of the interaction with the ocean, you can have circulation inside the ice shelf cavities, which creates important melting at the base. And finally, there is main melting happening at the front of the ice shelf with interaction with processes that happen at the sea surface, especially waves, which will be the main topic of the second part of this talk. The second mechanism is called calving, and calving happens when the ice shelf becomes thin enough that the crevasses can join and lead to mass removal at the front, which leads to creation of what we call icebergs. And I want you to sign notes here. When I say iceberg, you probably have something like that in your minds, like a very tall iceberg with a very long keel and a small sail on top of that. But if you put something like that in the water, it will just flip instantly and look like that. And so in real life, please remove this image from your mind when you think about icebergs, because icebergs are flat and also dirty. Sign not closed. Calving is a complex mechanism. It can happen at very different scales. Here you have two images. On the left, it's an image from the Twain Glacier, which is located here. And you can see, if I play the video, that the ice shelf is flowing from right to left. It's calving in this region, and you can see that it's calving with a very regular pace. And the icebergs that are created are like around 1 kilometer long, so like very fast, very regular calving. On the other side, you have the Ross ice shelf, which is this ice shelf here. And this is an image with a very different scale. You see 100 kilometers there. And so the crevasses that you see here are 2 orders of magnitude longer than this one there. So the calving that will happen for this ice shelf will be like much lower frequency, but much larger also. Something good. This is a map of Antarctica by Ringo et al. In 2013, when they compare how much these two mechanisms, melting and calving, account for mass loss for all the ice shelf. So for each circle represents an ice shelf. When the circle is black, it means that it's driven by melting, and when it's white, it means it's driven by calving. And you can see there is ice shelves which are mainly driven by melting, and some other ice shelves which are mainly driven by calving. And so these two processes are really important for ice shelf in general. And in this talk, we're going to be interested into the Ross ice shelf, which is this ice shelf over there, called Orbitite. Its area is around 0.5 million kilometers square, so it's the biggest ice shelf in the world. And to give you an idea of how big this thing is, this is the size of Texas in comparison. And for my fellow European nationalites, it's the size of France. So very huge ice shelf. And for this ice shelf, there is 50 gigatons of mass which are dumped into the ocean due to melting, and 150 due to calving. So both mechanisms are important. Finally, something else I want to point out to ice shelf. I will use this figure from Thomas and Backel in 2017 when they mapped the speed of the ice inside the ice shelf. And you can see that as you go from the back to the front of the ice shelf, the ice is speeding. And that means the ice shelf is accelerating as it goes toward the front. But we know that mass has to be conserved. So it also means that the ice shelf has to thin as it goes toward the front. So if you were standing on the sea looking at the ice shelf, you will see the downward slope. However, Baker et al. In 2021 used satellite imagery and look at the front of the Ross ice shelf. Once again, this is the front of the Ross ice shelf. Each of these blue and red line here is one satellite transect. And this satellite is ISAT-2, which provides elevation. And if you plot, for example, this box in 3D, with X and Y coordinates as well as the altitude, you see the ice shelf here and the sea there. The ice shelf is flowing from the top to the bottom. We can see that it has, as expected, a downward slope, and we can even see some crevasses here. But if you look especially at the front, you see this spike, which is unexpected because I say we think that we're going to see a downward slope. But all these spikes show an upward slope. And that's the observation that led to the beginning of this study. And so if you read the title of this presentation, you all wonder what can lead to this deformation. It's obviously the foot. Or in more scientific term, it's an underwater pieces of ice that protrude below the water and push the ice shelf because of its buoyancy. So the ice is lighter than the ocean, so push the ice shelf up and create the observed deformation. So maybe wondering, okay, that's fine, that's a good story, but how can you create this foot? How can that foot can appear? So if we start with a very smooth, typical unrealistic ice shelf, and especially with an ocean free of sea ice, this allows to have waves that are created and can propagate. This wave will increase the amount of melt transport at the sea level, enhancing the melt at this location, creating a notch that looks like that along the ice shelf. The overhanging parts will be not sustained by anything, so will tend to fall because of gravity, leading to something like that with a very small foot. And if you repeat the process enough, you can grow the foot. You don't really grow foot, you just remove material preferentially at the top and so grow at the bottom. Obviously, I didn't add any mechanism there, but we know that first, this foot should deform the ice shelf, and also we know that there is melting between the ocean and the ice shelf, so all this foot will be rounded. So in reality, it will probably look more something like that, with the deformation and the round foot. If the foot grows enough, it can lead to extra stress in the ice, especially tension at the bottom, which can lead to creation of crevasses. These crevasses can grow until mountain break, and this is a calving event, leading to a new smooth ice shelf without deformation. and icebergs. And I want you to take a special look at the shape of this iceberg, especially this red profile. Imagine yourself standing on the ocean looking at an iceberg that's just flipped. And this is a photo from Justin Lawrence in 2019, which was taken in front of the Rosyth shelf of an iceberg that just calved. And I don't know what you think, but in my mind they look pretty similar. With this part being the surface of the ice shelf, so very rough, a lot of crevasses, and this will be the foot, very smooth thanks to the melting. Obviously that's only one example, and it's quite hard to go in front of the Rosyth shelf because it's very dangerous. But there is, maybe later I told you that there is some hope that we may go there. So is that the end of the story? Have we solved everything? Well, maybe not. Because there is another mechanism that will explain the deformation. So if you have a cold surface, which in Antarctica will be minus 20 degrees C, and a warm bottom of minus 2 degrees C, this creates some kind of temperature gradient inside the ice shelf. And in the same way that can break glass if you apply cold and warm at the same time, this will lead to tension inside the ice. And this tension can be shown, can be represented as the moments that bend the ice shelf upwards. However, we can also remember that because of the difference of pressure at the transfer of the ice shelf between the water and the ice, there is also negative moments. So combining these two mechanisms, we may think that at the front of the ice shelf there is an extra moment that we have to take into account, which can either bend upward or downward depending on this temperature gradient. And this process was imagined by Roger Buck, and we published a paper a few months ago about that, and it showed that depending on the characteristic of the temperature gradients and the front, you can have a downward bending or an upward bending. And so the question is, who is right? Professor Roger Buck with this frontal moment, or Professor Tilwagner with his foot? And if you want to bet, it's now. For my first part, I want to have two main questions that will lead it. The first one is, can a model reproduce the observation that we have at the front of the Rosyth shelf? And the second one is obviously, which of the two mechanisms is responsible for the deformation? So I'm going to start by showing some data, then the model I'm using, and then the results. So the data comes from ICESat-2, which stands for Ice-Clad Elevation Satellite 2. This is the type here. The way it works is by sending some photons from space to Earth and calculating the time it took to go back and forth. And fun fact about that, this satellite is sending 10,000 pulses per second, and for each of these pulses, there is 300 trillion photons that are leaving the satellite, but only 12 of them came back. So you need a lot of back and forth to map the surface of the Earth. But the main point of this satellite is that, please, go next. Thank you. Is that you can have very good accuracy of the surface elevation. And there is a wide range of applications, and the one we are going to use now is the land ice. So I took the data from Baker et al. From the paper from 2021, which is around 3,500 transects. I manually classify them, which means I remove all the bad transects, like the ones which are crevasses in the middle, missing data, just bad transects. And I remain with 1,000 of them, and out of these 1,000, 80% of them were showing the rainbow profile, and 20% were not showing that. And so this is a map of the Rosyth shelf again, but with all the transects that I kept from ICESat-2. And if we look at one specific transect, for example, this one, this is what it looks like. The data from the satellite give you the altitude of the surface compared to the sea level. And the way we plot it will always be with the ice flowing from left to right, and the front of the ice shelf being set at zeros on the right. Obviously, we are interested in the top part, so let's zoom on that. We can clearly see the rainbow modes, with the mode being this deep over there and the rainbow in that part. And from now and later, we just don't show anything below, but remember that's the surface of the ice shelf. Yes, sir.
I'm assuming the satellite did not detect the foot.
It can, but in very specific conditions. You can go through water if the water is shallow enough. So we have 4 examples of the circle ice, but not at the rotation. The model I will be using is the 1D elastic beam equation, which is just a beam that you apply a force on it. The main variables are W, which is the deformation from the horizontal. The thickness H is assumed to be uniform along the wall ice shelf. The first term on the right is the buoyancy that push up. The second term is the weight that push down. The third term is the foot force. So this is the way we parameterize the effect of the foot, which is a point force at the front of the ice shelf that bends upwards. And finally, we just say for the internal moments that the movements at the front of the ice shelf should be equal to this moment that can either bend upward or bend downward. You can solve this equation, and it's that. Don't ask me how to get that. But basically, the way it looks is just a decreasing exponential time the cosinus and sinus function. And depending on the parameter, that's what it looks like. I want to emphasize on the 3 main parameters, which are the moments I told you about, the foot length, which characterizes the effect of the foot. The longer the foot is, the more deformation you get. And finally, the deformation length, which just sets how long will be the deformation on the shelf. And so when I will be fitting transect using these moments, this is the 3 variable I will fit on because that's the 3 unknown. So coming back to the transect we had before from I said 2, it looks great, but we have 1,000 of them, so just plot 1,000 of them. And it's nice, we have like variation from freeboard to 20 meters to 50 meters. We have some profile with very high deformation in blue, which means that the height of the rampart mode is very tall, and very small deformation like you like here. So it's an interesting plot, but we cannot do really anything by it. You cannot plot fit the model. So let's just scale each transect, and for that I will just divide the vertical. I will just divide the z-coordinate by the vertical deflection and the along from distance by the deformation length. And if you do that, all the transect nicely overlap, especially in the rampart part, in the rampartmost part here. And you can see that the tallest the rampartmost is, the nicer they overlap. Obviously, all this white that you see here are just because of the scaling, because you divide by a very small value, and so the value explodes. And you can overlap the model, the output of the model on this figure, which looks something like that. And this is interesting because I only put the foot here. I didn't put any moments. In these figures, in the red line, the moment equals 0, which means by just the foot, you're able to get a very nice fit of the data, especially in the rampart mode part, with only taking the foot into account. But if we had the moments, which I did here, I add a negative moment with this curve and a positive in this curve, and you can see that it nicely captures the whole range of profile at the front. And so I think it's an interesting figure because it shows that for all the transect that we have, this simple 1D elastic model can capture the wide range of transect we observe. But I want to show some specific transect which I think are interesting by themselves. This is the first one. The data I showed green, the green dots, and the blue and white line are the output from the model. The blue line is when I feed the data fitting both the foot and the moments, and the white line is when I feed the foot but fix the moment to be zeros. And as you can see, both models do a pretty good job at fitting the data, but because of this extra degree of liberty, the blue model is able to get the deformation at the front much nicer. And so that's once again shows the same thing as before, which is the model is able to reproduce the deformation. The second transect I want to show is this one, which maybe seems flat at the first sight, but if we zoom on it, this is what it looks like. You can clearly see a rampart mode again, a small one because it's only half a meter tall, but there's clearly a rampart mode. But with an extra feature, at the front you have this downward slope. And in this case, the model with only a foot is really not able to capture anything. You can get roughly deformation, but not this extra feature. While the model with both the foot and the moments can capture both the deformation and this extra feature. And so this is a good example, an interesting example, because it shows that for this transect, you need the combination of a foot and a negative moment to create this deformation. So you need to have a foot at this location to observe this transect. But the story is not that great for everything. In this case, both models seem perfectly fine. They both seem to fit the data very well, but look at how they do that. The white model gave a very long foot with no moment, and the blue model gave no foot and a very high positive moment. And for this case, we cannot distinguish which of the two is right. They both seem fine. And so there is these 200 cases when we cannot discriminate between a foot or a high positive moment. And so to summarize all this data for all transects, I just split into 3 categories, which is moment dominated, foot and moment combined, and foot dominated. And as you can see, there is around 200 transects which are dominated by moments, and around 500 of them which are dominated by foot. But there is these 200 ambiguous cases where we will need better data to be able to split them between these 2 categories. And so the conclusion of who is right, well, I think everyone is happy, they're both right. It just depends on the cases. Both processes happen at the rotate shelf. It's just they don't have the same amplitude at every location. And so to conclude this first part, we have seen that the elastic beam model is able to reproduce nicely deformation, and that both the internal moments and the foot play a role in the deformation. So that's fine, but what are the implications of that? Can this deformation that we observe, this bending at the front of the shelf, lead to mass loss through calving? And this will be the main idea of the second part. I'm going to start by showing some interesting time series that I have, then a few more observations, and then let's dig into a little bit into wave erosion. So this is a map of Antarctica again, but all these transects this time are one transect from IceSat 1, so the grandpa satellite of IceSat 2, which gets much coarser data but have the advantages of being taken on the longer time range. So if we zoom on the rotate shelf, once again the rotate shelf, we can zoom on a specific location when there is 10 transects that overlap very nicely at the same location. And so for every of these transects, I can just manually ping where the front was for this transect. And from that, I can compute the advent speed of the front at this location based on the transect that I have. So what you see here is the advance of the front of the rose front in function of time. And the first thing what we see is that the front is advancing at a very nice and uniform pace. The slope here is the same as the slope here. But we should remember that for each of these points, we have IceSat 1 data. So we know what the ice shelf was looking at for every of these time steps. And we can look at that. So for the first point, this is what the ice shelf was looking at with a very nice rampart mode. If we go to the second point, the ice shelf advance, but we can also see that the rampart mode size increases. And as I continue, it keeps showing the same behavior. Until 2007, when we lose the rampart mode, and the ice shelf retreats. And that's typical of a calving event. So we know that around 2007, a calving event happened and break the front of the ice shelf, removing the rampart modes. As the time goes on again, the ice shelf advances, and we see a rampart mode appearing again at the end. So we have a clear example here of a foot growing, deforming the front of the ice shelf, and maybe helping or leading to a calving event that remove 1 kilometer of ice at the front. So this data is nice, but we only have like very few points on the span of 10 years. So let's try to include that. I look at the satellite Sentinel-1, 1A and 1B, which is equipped with a C-band synthetic aperture radar. And what this satellite is doing is taking very large and high accuracy pictures. And I constructed this map, which is made of multiple pictures from Sentinel-1. You can see that every square is 1 picture. And you can very nicely follow where the front is. And so I did the same thing then from IceSat 1. I just, for these 3 locations, manually ping where the front was, and for every image I had, which led to this 3 time series. The green goes with the green location, the orange with the orange location, and the blue with the blue. And we have the same result that in set 1, which is a very uniform advance as function of time. But with a much better time resolution and accuracy. The only difference between these three curves are the speed, which is not exactly the same, but around 1 km per year for all these transects. So we know that the ice shelf, the front of the ice shelf, is advancing at a pace of around a kilometer per year. But we are interested in melting and calving, so we miss some data here. And I want to explain why. So we know that the ice shelf, the ice in the ice shelf has some velocities. So it should advance at some pace. And in this case, the speed of the front is equal to the speed of the ice. But in reality, there is melt and calving happening at the front, so you remove material. And if you remove material, the speed of the front has to be equal to the velocity of the ice minus the calving/melting that is happening at the front. And so we have the front velocity from somewhere 1, and maybe we can get the ice velocity from somewhere else. And luckily for us, there is clean told that published a paper in 2020 about a field work they did in 2015, when they put 13 GPS stations at the front of the shelf. And luckily for us, 3 of these stations, blue, orange, and green here, are located very close to the front. I mean, like less than 1 kilometer. And so these three GPS stations can give you the speed of the ice, not the front, the speed of the ice, basically at the location of the front. And so you can compute the speed for these 3 locations, and this is the value that you have here. And the plus or minus is not the uncertainty, it's actually the temporal variability. So there is very small temporal variability. The ice advances at a very uniform pace. And so now that we have both the speed at which the front is moving and both the speed at which the ice is moving, which is in blue for the speed of the ice, and in white for the speed of the front. The difference for these 2 data has to be the amount of material removed from the front. And so you can see that for the first station, it's around 70 meters, for the second station it's 35, and for the last station it's 20 meters. So let's say roughly 20 meters along the front of the roadside shelf. So we know that, at best, we have 20 meters of material removed from the front every year. But the question is, how much of these 20 meters are the consequences of the deformation and the flux calving mechanism? Well, to know that, we have to know how much the foot is growing. And to know how much it is growing, we need to know how much wave is melting the front. And luckily for us, there is a parameterization that says how much wave melts in icebergs that have been created, and we may be wondering if it can be applied to ice shelf. So I took the sea surface temperature and the Ross Sea, the sea ice concentration, the wind speed, and I put that into the equation, which is from Gladstone in 2001. This equation has a linear dependence in T, a polynomial dependence in wind speed, and this term in sea ice, which is just a cutoff term, which means that when there is sea ice, there is no melt, because when there is sea ice, there cannot be wave, and if there is no wave, there is no melt. So if you plug these 3 data into the melt rate, you get this map. But obviously we don't have the time and spatial resolution, so we just compute the climatology of that, and as expected, we have a very low value in winter when there is sea ice propagating the ice shelf. However, when the summers go on and the sea ice disappears, the melting increases to reach a value up to 250 meters per year. Which, if you average on the whole year, gives you 60 meters per year of melting just due to wave. But we have just seen before that we have 20 meters per year at best. So this thing is not possible. We cannot have 65 meters. It makes no sense. So this means that this wave parameterization is just wrong and clearly overestimating the amount the wave are melting the ice shelf. So there is 2 possibilities for now. The first one is trying to improve this parameterization, which is what a student at the university is doing, namely Anya Waterman. She's having a wave maker in a cold room to try to see how much wave melt the ice. And the other way to try to solve this issue is to reconcile both to reconcile the melting we have with the parameterization. So let's just say that we divide the old made the 60 meter per year by 10, we get 6 meter per year of wave-induced melt. And if we plug that into the elastic beam equation, I'm not going to detail it, but we can compute how much the flux calving mechanism will be responsible to in terms of calving, and the answer is 14 meters. And if you add the two, you get 20 meters, which by a lucky coincidence is exactly what we are looking for. So hopefully this is just an upper bound. It means that in the best or worst case scenario, depending on how we see it, the flux calving mechanism will be responsible for 40 meters per year of mass removal at the front. So let's conclude this first part. We have seen that the ice shelf is advancing at a pace of around 1 kilometer per year. We have examples of calving mechanisms that have been facilitated by a foot, but we also saw that the wave parameterization is clearly wrong, and we cannot use it to investigate how much of this 20 meters is due to the foot or something else. And the sad conclusion is, even if 100% of this 20 meters were due to the foot, it's only 20 meters out of 1,000. So clearly, the flux calving mechanism is not important in terms of mass balance at the front. However, maybe we can use it for something else, like getting some insights into the ice property at the front using the deformation that we can observe very nicely. And I'm going to conclude on that. If you want some more details, you can look at the preprint, which is about everything we talked about today, but with much more details. And once again, here are the main summary of what we have said. And I'm going to conclude on that. Thank you.
Thank you very much. Do we have any questions? Yes, students first, and then John. Here we have.
Hey Nicolas, great presentation, super interesting, very nice graphics. I have a very naive question about the ice sheet. I have no knowledge about ice sheet mechanisms, but I'm wondering how the surface mass balance or precipitation, the impacts on ice sheet because of precipitation or moment could influence this, or there's not significant weight coming near that on the ice sheet.
What, like in terms of how much the snow and the firn is deforming the ice shelf?
Well, how much of that would play a role in a simple model like this?
Oh, well, I think the main thing is like the firn and the snow apply to, that you have to take into account in terms of density, because the density of the ice shelf is not the density of the ice, because you have this layer of firn and snow, so you have to reduce the density of the ice. And when you do that, you just have a better fit with the data. So I think that's the only way we take it into account. But if you want to get deeper into it and do a more like a 2D, more complex analysis of it, you will have the viscosity of the ice will be not uniform the wall shape, but will vary by depth. And I think that will be the main thing to take into account.
Hamish.
At the end of your talk, you had your wave-induced melt, and you divided it by 10. Is there a reason why you think that's 10 times greater than what it should be in reality?
Because it works.
Right.
No, I mean, so I picked this 10 just because it gives 6 meters, and if you get 6 meters, you get 14, and if you do 6 plus 14, you have 20, which is what we look for. So I picked this divided by 10 to get an upper bound of how much melting and calving would be responsible by the flux calving mechanism. That's the only reason, just to get a fitting upper bound. Because we know that the melting is wrong. It has to be wrong because the data we have with these 20 meters per year are like very high accuracy data. So just find a way to get some information about the flux calving mechanism. That's the best we can do.
Is that a question you used in previous studies? Like, is it established equation people use that wave-induced melts?
Yes, that's.
Because that seems like a pretty big
This one.
drawback. Yeah.
There is only this one.
Okay.
And it's completely made up.
So the project that he's funded on is primarily motivated by how ill-constrained this melt parameterization is. That was the driving force behind this NSF project. And we didn't realize how bad it was until we plugged it in, and it's actually worse. Yes, Clark.
I have a question. So Is all the melt that you're talking about here just from the front?
Yes.
So the melt from the basal melt and the surface melt is irrelevant, or you just think it's much smaller, or it just doesn't have as much to do with the,
So it's totally irrelevant.
okay,
I just didn't consider it because that's too much.
okay.
And it's really relevant in terms of mass balance because you remove a lot by just melting the ice and the snow. And it's also relevant because you're changing the shape of the ice shelf. Because the way it flow and the way it flow with melting will be not the same.
Right.
So that's the two ways it's relevant.
So you would expect, so the 20 meters per year or whatever that you had, so we would expect that the calving and front melt should be even less
Yes.
than that, because some of that is coming from others, okay.
No, because
No.
what we're looking at is just what is happening at the front.
Okay.
And so what is happening at the front is this 1,000 meter of advance and 20 meter of material removal. And there is also some other X amount of melts at the top and at the base.
Right.
John, sorry. Yeah, really excellent presentation. To let an idiot like me understand most of what you're talking about was really great. The difference between the foot model and the non-foot model, I forget what that one was called, does that have anything to do with, let's say, seasonal storm activity in the adjoining ocean? So in other words, if you have more, I'm just imagining if you have more wave activity in a stormy season, you might carve out that foot a little bit more regularly in that year than you would in a year that goes by without as much storminess. Is there something you can do to figure that out, or is that not really plausible?
Clearly the answer is yes. I have no idea how to investigate that. And in fact, there is like, if we in this presentation, I assume that the rate of growth of the foot was perfectly equal to the amount of wave erosion that you had at the front.
Okay.
Which in fact is not true, because you also have melting of the foot, and you also have the breaking of the foot. So there is all of these kind of different mechanisms that you should need to take into account to have a very clear time evolution of the foot, and having a proxy for the wave intensity through storms will be, yes, very interesting. It was just too complicated for what we are hoping to do.
Okay. Thanks. Really great presentation.
And part of the issue with this is that the wind dependency here is local, right?
Yes.
And a lot of the wave activity might be remotely generated, right? If you have storms.
True. That's right.
In the far field, it will send you large waves coming through, which you don't
I also
actually
wonder
want.
if storms in the summer may make more of a difference, because in the winter you have your pack ice out for you, your facets
Yes.
stuff out so far
Yeah.
that you're not touching the ice shelf at all. I mean, even the summer it's so damped, right? Like the surface of the Southern Ocean can just look like glass. It's crazy.
Yeah. And at least in terms of occluded cyclones, we recently discovered there's almost no seasonal variation around Antarctica.
Right.
And that's not true in the northern hemisphere. There's a huge seasonal variation in those intense cyclones. So I just wonder if there isn't something to that, you know, the seasonality of the surface and the not so obvious seasonality of the storminess might be a factor.
Yeah, I think it's really complex to figure it out. It's a cool idea.
And we don't have the accuracy of the model to be able to include seasonality. That's why I always do the thing is meter per year, because we are not accurate enough in terms of wave melting to look at seasonality.
Yeah, you don't have enough frequency of the ISAT2 to do it in a 1 week time period or something, right?
But with these data sets, we can have data every few days, so with Sentinel-1. So I didn't use all the data I had available to do that. Actually, you can put much more dot on this curve that there is now, just that it took a long time because you have to click at every photo, so every location it takes a long time.
Yeah.
But you can get a very good accuracy just from this one. And that's probably the best.
Hannah.
Yeah, so sorry, did we? So you know you have those ambiguous cases where you can't tell what.
Yes.
Is there a set of observations that you think would be useful to help tease those apart? Besides maybe it is just literally going and looking for feet. Or is it something that, even if you had that, you wouldn't be able to tell just because you have 2 free parameters and good luck?
Well, sorry.
Yeah, go ahead. I was just wondering if there's a way to constrain that.
So the way we can do that and the way the model is actually doing that, which I didn't talk about, is that when you add elements, you can play with the curvature at the front. And which the foot does not impact at all. There's zero impact on the curvature. So if you have a good representation of the curvature at the front, you can guess exactly what the moment is just based on the curvature. There is a direct relation between the curvature of the front and the moment applied at the front. So if you get good data through satellite, through airborne measurements or anything else, just of this part, you can guess or understand what will be the moment of the front.
And so the one thing that Nicolas did not mention is that we've been talking with Roger Buck, and we actually have recently submitted a joint proposal to the Keck Foundation to go to the Ross Ice Shelf and measure the front underwater, because it's never been done. And the Keck Foundation is special because it supports research that is not being funded by standard agencies.
Right.
And we have proposed this trip to the NSF before, and the NSF said, too many people are gonna die. So we're gonna go to some rogue philanthropist, with less red tape.
Can I ask another somewhat related question to this? Is it the foot or the moment that might result in more catastrophic, and by that I mean newsworthy calving events?
None.
No, it doesn't, no difference?
No, so if I had to answer, I would say the foot, because the foot imply...
It's more hidden ice, right?
The applied stress on the foot is further away from the front, so it leads to calving, longer calving, because the stress is applied further away.
Yeah, okay.
But both will be small compared to the giant calving event that will probably be important for this session.
Okay.
However, especially the faux ones rotate immediately.
Yeah.
And so there is a video of the Palmer icebreaker being pretty close to the Ross Ice Shelf, and one of these calving events happened, and they got actually a bunch of ice just tsunamied onto the deck with it, did some damage. So that's one of the reasons why NSF doesn't want to go anywhere near it anymore. Yeah. And so the idea now is that we're going to take a remote. No, we're going to take a remotely operated vehicle.
Oh,
That's reasonable.
Rather than go close and personal.
Very cool.
More questions.
Any more in the back? Okay.
Going again. So you have this for the Ross Ice Shelf, right?
Yes.
But then you kind of showed in the beginning, like the smaller calving events and how this isn't necessarily applicable. Like in the way beginning when you had the video.
Sorry for that.
Gotta go all the way back, I'm being like a real jerk here. Does this apply then in those contexts, or do you need an entirely different model for like the smaller, faster like that versus the big things on the Ross Ice Shelf?
Well, in this case, we feel that it's calving like every few days, probably a few weeks.
And they seem smaller, right?
So even if the properties were right for it to grow, you would not have time.
Right, so there's probably like a different model that you would need to understand
totally.
calving in this region, so it's very dependent on where you are, that's all I'm asking.
Yes, that's what this figure is showing, but depending on which ice shelf you're looking at, the calving will be like not the same.
Are there other parameterizations out there, like do people work on understanding the calving of that as well? Right?
They look at the way crevasse propagates, how well going to crevasse, how if you're like how spread out the crevasse, how far away, if there is like subsequent crevasses.
Yeah.
Come to my talk at AGU
Doing it here to tell us the
Wednesday
rest of it.
afternoon. I'll talk about full depth calving. Yeah.
Alright, cool.
Hamish.
You quickly mentioned crevasse propagation here. Have you ever considered that for the Ross Ice Shelf, that as crevasses gradually get towards the front, if they're propagating, will it mess up your model?
Well, I didn't do that because it will make the model much more complicated. Like you cannot do one thing with crevasses. And you can, but it will be not a straight. You have to parameterize in some way the crevasse propagation into your ONG. And as you can see in this figure, the crevasses on the ice shelf are like hundreds of kilometers long and probably hundreds of meters large. So it's just not the same scale and not the same.
Like I wonder if in front of one of those large crevasses, if the median is significantly different. Surely it would be.
Yes. And when I manually classified all the transects I had, I could see some transect with crevasses somewhere close to the front. I just removed this one because it was too much thing to be able to add in the model.
And what he's looking at is really just the very front couple of kilometers, right? And so even something like this here doesn't necessarily impact, that's what is that, 30 kilometers or so, so you wouldn't see necessarily a signal of that. But, 98% of those ice shelf gets removed by these giant tabular icebergs that come off these rivers.
So that's the conclusion of the talk. It's interesting mechanism, but not in terms of amount of mass removed.
Anything else? All right, then let's thank Nicolas.